Alrighty, we are at Math Tidbits number 10. Seems like we should have some kind of celebration or something. And I'm going to cover pretty briefly an important subject, differentials. It's commonly helpful, and this follows very much on the heels of our number 9 video on approximations. It's commonly helpful to be able to approximate the change in some function f of x when x is changed to x plus delta x. So we want delta f when x goes to x plus delta x. And any number of times this comes up. This comes up in error analysis in lab. This comes up in quick estimations of changes in a particular function. Kind of related, actually, to some of what we talked about, like I said, in the approximation video. So we're going to define, as we did before, delta f to be f of x plus delta x minus f of x. And again, as in the last case, Taylor comes to the rescue, and we want to take and figure out what f, we want to know what f at x plus delta x is by knowing what f at x is. So we're going to apply Taylor in this way. We know what f of x is and all its derivatives are at a given location. And the Taylor expansion as applied here will look something like this. Okay, so if delta x is small, then delta f is well represented. And the beauty of knowing Taylor's series is you can go to the next approximation if you need to. But if x is really, really small, then delta f is well represented by f prime of x times delta x. It is only an approximation, as I said, but it may oftentimes be really, really all we really need. So I'm going to take and, just to illustrate this for you, take f and plot it versus x. And let's say that in this region here, f looks like this. So this is f of x. And we're interested in this location x. And we want to know what happens to f if x becomes x plus delta x. And so, if we want to be exact about it, we would say, well, here's f at x, and here's f at x plus delta x, and the difference between those is delta f. And what we're doing in taking the approximation, where we've taken the derivative of f at x and used it, is we are saying, I'm going to take the tangent line here and do my best visual derivative. And say, all right, here's the tangent line. That's pretty good, actually. And when I take that tangent line, what I am finding here is that this little guy, remember this slope is equal to f prime at x. This is f prime at x times delta x. And you can see it's not quite the same. F prime at x times delta x is not equal to delta f. It's not crazy far away from it. Well, I don't know. It's 2/3 of delta f. So okay, it's crazy far away. But if we take the limit as delta x goes to 0, then what we get is this. We get df equals f prime dx. Because as delta x goes to 0, then delta x can be replaced by dx, and delta f gets replaced by df. If you want, one of the things you mathematicians don't like if we do, but to be honest, the inventors of the calculus did this anyway. You'll note that f prime of x then equals df divided by dx. So it really is, it really is the infinitesimal change in f that is begotten by an infinitesimal change in dx. This comes about. This is really, really useful. So if you know what the functional form of a variable is, and you know you're changing your independent variable by a certain amount, you can get a good approximation for a small displacement in x in your independent variable. You can get a good approximation of the change in delta f in f simply by taking the derivative at that point and multiplying by your change in your independent variable. Really, really nice for quick approximations. It's also very useful, and we will not get into this in this semester, but you will in Calc 2, and you will in the second semester. We'll need to change variables of integration sometimes. And when we do that, we use this very idea. All right, so I'm going to put this in red. Integration warning. Haven't done anything on integrals yet in these math videos. But for those in the know, I do want to show you how this can be used. So suppose we won't be doing this for a long time. Like I said, we won't be doing this in this semester. Suppose I want to know the integral from a to b of x e to the x squared dx. One of the ways in which we can do this is to do a substitution. So we substitute t equals x squared. And when we do that, we can find out, all right, well, if this is the relationship between t and x squared, what's dt then for a given dx? In other words, what's the thing I'm going to have to use to convert this integral into an integral over t? Well, dt is going to equal the derivative of t with respect to x. It sounds kind of funny. that's just 2x, and then times dx. So when I replace dx, I'm going to need to replace dx by 1 over 2x times dt, and x is equal to the square root of t, right? So this will be equal to 1 over 2 times the square root of t dt. And so now I'm going to use this to replace in this integral. This integral now becomes integral between two times that correspond to xa and xb. X is the square root of t. This exponential becomes e to the t. And then dx is replaced by dt over 2 times the square root of t. And finally then, that integral becomes integral from ta to tb, 1/2 e to the t dt. Easy integral to do. It will just be 1/2 e to the t b minus e to the ta. All right, anyway, that differential that we used here is just the justified by the arguments we made above that related first finite changes in f to finite changes in x, and then taking the limit to the infinitesimal, we then come up with the idea of this differential. All right, so that's that for this Math Tidbits video, and see you for the next one.